Here the step down converter for our load we are studying here. So here we are having supply, Vs, value is Vs. If you consider this chopper or a switch is ideal, this waveform is true. Okay. And in this waveforms, if you write the source voltage, if you measure the voltage in between these two terminals, and if you call that its instantaneous value is Vs, so I should draw the waveforms here. Okay. What is a Vs? Vs is this value. What is the value? Its value is Vs. An example, this is capital letter Vs I am using to denotes constants. Okay. For an example, if it is 10 volts, 10 volts. Instead of 10, I am writing letter V suffix S, capital letter. The small Vs says that it is instantaneous values of the source side voltage with respect to T, with respect to T. Okay. So this is a axis, okay, this is source voltage, it's constant. Okay, is constant. What is the value? Vs. Okay. So this is T1, correct? No, time is T1. This is how much exactly? This is T1, or I can say KT. But you can see that source voltage is constant. Vs is constant. Starts here. So now this is V0, correct? This is, if you call this as I0, it is correct. But one thing I will tell you, this V0 is Vs if you consider chopper loss is 0. If you consider there is a loss across chopper, and if you call that as a V chopper means if it is a 2 volts drop, V chopper becomes 2 volts. If it is a 1 volts drop, V chopper becomes 1 volts. Then what is this? It is not Vs. Instead of that, I should write as Vs. I should write this as Vs minus V chopper. Instead of this, I should write Vs minus V chopper. So this also, instead of this, I should write Vs minus V chopper divided by R. This height becomes Vs minus V chopper divided by R. Means if it is 20 and if it is 20, for an example, if this is 2 volt and if this is 20 volt, 20 minus 2. This height becomes 20 minus 2. This height becomes 20 minus 2 divided by R, because Out of 20, 2 volt is dropped here. 2 volt is dropped here. In these points it is dropped, and remaining 18 volts comes here. So if you current whatever is flowing is 20 minus 2 divided by this resistance Xi naught. And if you plot Is is the current which is flowing somewhere here, source side. I can call this as Is. This is Is. This is I naught, correct? See, Is and I naught are same, one and same. That's the reason Is is also same as your I naught. I naught. Same thing. So what is this side? What is this side? This side is same as Vs minus V chopper divided by R. So we should keep in mind, this is my Vs is constant, its value is Vs, source voltage, output voltage instantaneous values, it takes a magnitude of Vs minus V chopper and 0. I naught, output current instantaneous, Vs minus V chopper divided by R, 0. Source current instantaneous, Vs minus V chopper divided by R. If V chopper is 0, then it becomes Vs, this is also Vs, this is Vs by R, this is Vs by R. This we should keep in our minds. So now we will study more about DC to DC converter step down operation for our loads. So we can see here, this is a DC to DC converter, the input voltage is Vs, correct? The input voltage is Vs. We need to consider that there is a DC source here, its value is Vs, its value is Vs. So what is the value? It is Vs, yes. Next, so last class in the previous discussions we learned that what is an average value of the load voltage. So what is an average value of the load voltage means average value is K into Vs, where K is duty cycle, K is nothing but what is the K formula? T1 by T, T1 by T, on time by T. Okay, see, average value means if you keep a DC multimeter here, what is the value it show you? That is an average value. Sorry, DC voltmeter here, what is the value it show you? That is average value. Yes. Then there is one more term, the effective input resistance seen by the source. I will write here the effective input resistance, effective input resistance seen by the source, seen by the source. We'll use the term Ri. See, this is the resistance of these circuits. what is the resistance of this, effective resistance of this source, if you see from this end, if you see from this end, seen from the source, or seen by the source, so that is we need to calculate. Okay, so what is an average value of the load voltage? Average value of the load voltage is K into Vs. What is the source voltage? Source voltage is Vs. Source voltage is Vs. See, source voltage is this voltage, these two terminal voltage is Vs. Source voltage is Vs divided by average current, I average. IA is nothing but, what is this? IA is average current. So IA is average current. Okay. So what is the average current? IA is nothing but average voltage divided by resistance. What is average voltage? K into Vs divided by R. So that's the reason. What is Ri? Ri is nothing but, so Ri is nothing but Vs divided by IA. IA is nothing but VA by R. VA by R is K into Vs divided by R. R cancel each other. Vs cancel each other. So R by K. So effective resistance seen by the source is R by K. So Ri is R by K. So this is our effective resistance seen by the source. See, one thing I will tell you, if you change the duty cycle, K is equal to 0.5, if you R is equal to 10 ohm, R is equal to 10, for an example 10 ohm, if K is duty cycle, then what is an effective resistance? 20 ohm. If R is 0.1, then it is 100 ohm. So what I am saying, the Ri will change, effective resistance seen by the source will change when you change the duty cycle. Okay. Next. So this kind of circuit works in two modes. See here, we have studied that. What is the VA formula? Again and again I will write VA. What is that? K into Vs. K is what? T1 by T. T1 by T into Vs. So if I want to change average, what I need to change? I should change T1. Correct? Yes. For an example, if the switching period T is 1 milliseconds, if you choose T1 is equal to 0.5 millisecond, then my average becomes how much? 0.5 by 1 is 0.5 into Vs. So half of the Vs. If I want to increase VA, what I should do? The T1 I should change. T I should keep constant. If I want to reduce, T1 I should reduce, T I should keep constant. So this is actually, here T is constant and on time we are going to vary. We are changing the on time and we will keep T period of the switching we keep constant. So this is constant switching period operation, commonly known as constant switching frequency operation, or else we is popular as constant frequency operation. So constant frequency, which frequency? Switching frequency. Actually this term is this kind of method, this is one method we call as constant frequency operation. In a constant frequency operation, switching period we keep constant. To vary the load, average load voltage, we need to vary on time. This is also called as PWM method, pulse width modulation methods. So constant frequency operation. And there is another method like variable frequency operation. Variable frequency operation. So what is that variable frequency operation? See here, ultimately I should change T1 by T. This factor should change. So one method, as we have seen so far, T1 I should change, T I should keep constant. Another method, T1 we should keep constant and T we should vary. This is also possible. See here, for an example, if you keep T1 as constant like 0.5 millisecond, VA is always formula is T1 by, VA is T1 by T into Vs. So this is, so assume that we are keeping constant this point, we are keeping T1 as 0.5 milli and T as 1 milli and Vs is 10 volts, we got 5 volts. And another, if I want 4 volts, 0.4, if I require 4 volts, I can achieve in this way. In previous case, I should make this as 0.4 and I should change this to 1. Otherwise, what I need to do? Tell me. So, somehow what we need to do, this factor, you can keep this 0.5 milli. This is 10 constant, Vs is 10 constant. Va should change to 4, means something I need to do it. 0.5 by 0.5 milli by x should become 0.4. What is the next value? 0.5 by milli by 0.4. What is that? X. So 5 divided by 4 means how much? 5 divided by 4, 1.25. 1.25 milli should be x. So if you choose this as 1.25 milli, see what happens, check. 1.25 milli, 0.5, so 0.25, 0.25 goes how much time here? This is 5 times, this here twice, it's 5 here, this is 2, milli cancel each other and answer becomes 4. So what I should do? I should choose T is 1.25 milliseconds, means frequency should be 1 by 1.25 milli, means something 1 by 1.25 k. How much? 1 by, what is the value of 1 by 1.25? Can you calculate, all of you? So what is the value of 1 by 1.25? 1 by 1.25 is 0.8. So I should choose 0.8 into 1000 means 800 hertz. So I should change the frequency of switching frequency to 800 hertz and I should keep this on time as same as 0.5 millisecond. In this way also we can get a 4 volts. This is here the frequency of switching frequency is variable. We are varying the switching frequency. That's the reason this is variable frequency operation. Variable frequency operation. Variable frequency operation. So there are two terms, two methods to implement the DC to DC converter. One is constant frequency operation, operation, another one is variable frequency operation. So in the constant frequency operation, on times we change and frequency or period of the oscillation we keep constant. In the variable frequency operation, frequency we vary and on times we keep constants. So most generally used is constant frequency operation. Next, we will solve one problem on this DC to DC converter. He said DC to DC converter has a R load of 10 ohms and input voltage is 220. Okay, so what is the voltage here? He said is he is saying that it is 220 and R is how much? 10 ohm. R is 10 ohm. Then when the converter switch remains on, its voltage drop is 2 volts. So he is saying that when the switch is on here, it is not ideal switch, so there is a drop of 2 volts. Okay, then and the chopping frequency or switching frequency is 1 kilohertz. He is saying that switching frequency is F is 1 kilohertz. 1 kilohertz. So 1 kilohertz. Okay, then and duty cycle is 0.5. So K is 0.5. K is so K is 0.5. K is 0.5. So then determine the average output voltage. So the average output voltage, what is the formula for average voltage output? VA is K into Vs. K is how much? 0.5. Vs is how much? 220. So what is the value? Vs, Va is 110 volts. Average voltage is 110 volts. Then what is the next question? The RMS of the output voltage. So RMS of the output voltage, this part. So what is the formula for RMS of the output voltage? V RMS of the load. We call like this, or in textbooks we call as V naught. Anything is okay. So what is the formula for RMS of the load? You have seen already. Okay, so what is the formula for RMS of the load? RMS of the load formula is root of Vs into root of K, or root of K into Vs. Okay, root of K into Vs. So that's equal to root of K is how much? 0.25 into 220. So this is how much? Root of I think 0.25, it seems 120. How much is how much? RMS is not 110. So what is the value for RMS? Okay, sorry, I made some mistakes. Okay, this is actually correct. How much? So what is point 0.25 into 0.25? 0.65. Okay, one mistake. Okay, I will tell you. See, one mistake what we did here is we have consider it as ideal, but I said already it is not ideal. What is the drop here? Drop is 2 volts is there. So this formula I should change. So instead of K into Vs, I should write it Vs into V chopper, because this formula we got K into Vs. We assumed earlier that there is no loss. If there is a loss, Vs 220 minus 2 comes to load. That's the reason here 220 minus 2 comes here. Okay, then it is 0.5 into 118. How much it is? Sorry, 0.5 into 218. So 109 volt. 109 volts. Then again here also root of K, RMS of the load, root of Vs minus, if you assume that this is 0 drop, then it is root of K into Vs. So Vs won't come here. What is coming here? Vs minus 2 comes here. Let's say here Vs minus V chopper we should write here in a common formula for a lossy chopper. Means if this chopper loss if you consider, then I should write 220 minus 2. 220 minus 2. Okay, then we'll write root of 0.5 into 118. What is the value? Value is, if you calculate this, 154.15 volt. 15 volt. How much? 154.15 volts. This you verify in your calculator. So this is a RMS of the load voltage. RMS of the load voltage. Only difference here is, instead of Vs, we have considered Vs minus 2 because he is saying that there is a drop across this. Yes. Next. So summary is, so VA formula, if you consider a chopper loss, becomes K into Vs minus V chopper. So we'll rewrite, VA formula is K into Vs, VA formula is K into Vs minus V chopper. V RMS of the load is, in means if you consider a chopper loss, I should write root of K into Vs minus V chopper. In this case, V chopper is 2 volt in my question or in my example. Vs is anyhow 220. Vs is 220. K is 0.5. I should substitute 0.5 here. That's all. This is what we did so far. Next part. The converter efficiency. Converter efficiency we can calculate. So the converter efficiency we can calculate using a formula. You can write, I will see. Converter efficiency. Converter efficiency. Converter efficiency is P0 output power by input power. So what is P0 now? What is P0? P0 is, we need to calculate. Okay. So what is the formula? 1 by T. So 1 by T integration P0 1 by T integration 0 to T1, correct? T1, 0 to T1, 0 to T1. So then output voltage. Ideally this is Vs. In my cases this becomes Vs minus V chopper, correct? V chopper, because we are considering the chopper loss. So it is Vs minus V chopper, that is voltage. Then what is current? This is Vs minus V chopper divided by R. Okay, so Vs minus V chopper divided by R into dt. So this is 1 by T 0 to T1. Vs, source voltage value is Vs, V chopper is 2 volt. V chopper is 2 volt. You can say always you can write as V chopper only, V chopper only, V chopper. We'll substitute later. And again here Vs value is Vs, V chopper divided by R to dt. So all these are constants, so that what happens? Vs, capital letter Vs, V chopper whole square, because this into this, divided by R, and in the denominator 1 by T is there, into dt, integration T 0 to T1. This becomes Vs, V chopper whole square divided by R into T1 by T, on time by this. So what is this? Vs, V chopper, Vs is, we'll substitute all the values. Vs is 220, V chopper is 2 volts whole squared divided by R is 10 ohm. T1 is, T means K. K is how much? K. Okay, K. So this is 220 minus 2 whole squared by 10 into K. K is how much? K is 0.5, 50%. So this is a value. So 220. So this output power is 2376.2 watt. Nearer to that value you will get. So this is how much? 2376.2 watt. Okay. Next, we'll calculate input power. As usual, we should take average T 0 to, we have seen already while calculating the input power calculations. See here. So Vs into Is into dt. So Vs by R T 0 to T1, why you have taken? Because my Vs by R is existing only from 0 to T1. Current is existing only in on time. Input source is there, Vs is there always. So we should take this formula, 0 to T1 Vs and Vs by R. But this is earlier we have taken where we assumed that the chopper loss is 0. Here what is an instantaneous values of the source voltage? Instead of Vs, source voltage is same, Vs. What is an instantaneous values of the source current? Source current means what? Current, entire source is not responsible for current, because from that source Vs, some drop occurs while current is flowing through its switches. That is how much? 2 volt. So 220 minus 2 is responsible for current. That's the reason I should write Vs minus V chopper here. So what I should write? 0 to T1. See here, 0 to T1. Here the source voltage value is always Vs in ideal case. In my cases, if I consider the drop here also, the source is same, Vs. Source voltage is Vs. Correct? Source voltage is Vs. But source current is same as this. I said already, this is a plot of I naught, or else I can use this for a plot. This is also a plot of Is, because this current and this current is same. This current and this current is same. So this is what the current for this entire current, entire voltage I should consider, and the resistance. This is supply Vs, this is drop, this is 2 volt drop is there. So total resultant voltage is how much? Vs minus V chopper. Vs minus V chopper divided by R is responsible for this. Divided by R is responsible for this. So responsible for this. That's the reasons. So source voltage, actually strictly speaking, this is instantaneous source value and instantaneous current value into dt. So 1 by T, the instantaneous source voltage is always Vs. Instantaneous source current is same as load current. That is how much? That is Vs minus V chopper divided by R into dt. That's the reason 1 by T integration 0 to T1. So Vs you can okay, I will write. So Vs minus V chopper divided by R into dt. This I can say Vs I will keep outside. Vs minus V chopper divided by T divided by R into dt, integration T 0 to T1. That is Vs into capital letter Vs into Vs minus V chopper divided by R. This T cancels R divided by T. T1 means KT, because here T integration becomes T1, anyhow 0. T1 minus 0 is T1. T1 is in sense KT. So that T cancel each other. That's the reason Vs, then Vs minus V chopper divided by R into K. So what is the final formula? Okay, this Vs is how much? 220. Then 220 minus 2, because V chopper is 2 divided by 10 into K. K is how much? 0.5. So this is 220 118 divided by 10 into 0.5. This is how much? 2398. 2398. So what is the converter efficiency formula? I said is P naught by Pi. What is P naught? P naught we have already calculated. This is a value 2376 2376.2 watt. What is PI? 2398. We have already calculated here, 2398. So this is a converter efficiency formula. So it is how much? 99.09, because you got, I think, 0.9909. So this is in percentage, we can call like this. This is a converter efficiency. And what is the last part? Last but one, it seems. The effective input resistance Ri of the converter. What is the formula for that? What is the formula for effective input resistance? Ri is R by K. This is the formula, correct? R by K. This is R by K. So you use that formula. So effective input resistance Ri is equal to R by K. R is 10, 0.5, so 20 ohm. Then, so what is the last part? This is also enough, but there is a last part here. The RMS value of the fundamental component of the output harmonic voltage. This, if you are able to remember, remember. Otherwise, if you feel it is difficulty, you leave it. So we already learned that in Fourier series, the output, any waveform, I can write in terms of DC component and AC components. Here, using that Fourier series analysis, the output voltage we not writing like K into Vs. This is DC component, average value, and Vs and rest harmonics. Vs by N pi, then summation N 1 to infinity, summation N 1 to infinity, sin 2n pi k, sin 2n pi k plus into cos 2n pi ft, cos 2n pi ft plus Vs by n pi summation n is 1 to infinity 1 minus cos 2n pi k sin 2n pi ft. So this is, so if you want to calculate fundamental component, means first harmonics, we one, I can say V1 of t, first harmonics, K is 0.5, Vs is 220, S is 220, N is 1 by pi, only one thing I will say, N is equal to 1, so N sin 2 pi K so cos 2 pi ft, cos 2 n is 1 pi ft plus again 220 by pi, n is 1, 1 minus cos 2 pi k sin 2 pi ft, sin 2 pi ft. So this is 110 220 by pi sin 2 pi cos f is what is the switching frequency as given, 1 kilohertz. So 1000 t. So anyhow, I require only, I require on this part is not required because I require only fundamental harmonics. This says that my Fourier series consists DC component and as well as rest harmonics. I am interested about only fundamental harmonics, so this DC component I am not worrying right now. I am not using, only fundamental component we are thinking. Okay, so it is 220 by 2 sin 2 pi f is 1000, this part, t, how much it is, how much, 140, value is finally 140.06 sin 6283.2 t, this is 99.04 volt, means 99.04 volt. Okay, thank you.